In the human brain, the vision system is co-located with the central compute. Machine vision need not be built in the same way. Experimental farms, for example, are exploring computer vision done at the edge on individual low-powered devices which can report back independently to a central server. This is Data Skeptic Consensus, and the 28th installment in our series about how multi-agent systems achieve collective decision-making. Today on the show, I'm joined by Karthick, Shankar, and Somali Chaterji to discuss the paper JANUS, Benchmarking Commercial and Open Source Cloud and Edge Platforms for Object and Anomaly Detection Workloads.
I'm Karthick Shankar. I am a master's student at Carnegie Mellon University, and I'm studying computer science. I previously did my undergrad at Purdue University studying computer engineering, and I worked with Professor Chaterji at the Innovatory for Cells and Neural Machines lab.
I am Somali Chaterji. I'm an assistant professor in the Department of Agricultural and Biological Engineering, which is in both colleges of engineering and colleges of agriculture at Purdue University. And I lead the Innovatory for Cells and Neural Machines, which is called ICANN. And we do both applied machine learning in computational genomics on the one hand, and cloud and IoT on the other hand.
Maybe I'm just not close enough to the loop of things, but I think it might be a little atypical to have those two departments so close together. Are you guys pioneers in this space, or has this been an ongoing trend?
Yeah, so I would say ag and biological engineering is my home. I have a background in both computational genomics and computer science. So my PhD was in bioengineering, and then my postdoc was in computer science. And because in my department, AB, which is, by the way, number one in the country, they really like to see applied computational algorithms being applied to both the sides of the department. So we have an agricultural side in which my specialty is digital agriculture, and we have a biological engineering side where my specialty is computational genomics. And the way the two of them are kind of tied together is applied machine learning. So it's applied data science and engineering lab applied to both domains of genomics and IoT and edge analytics.
Well, it's easy to think of some of the techniques of machine learning applied to digital data. I do lots of episodes on stuff like that, but agricultural data is not quite so digitized, or maybe it's more digitized than I know. What does it look like in terms of sensors and devices if I were to go on a modern farm and really see what's high tech? What's the current state of things?
Internet of Things is pretty much booming in the space of agriculture, right? And all of these sensors are getting smarter and smarter, especially things like temperature sensors, humidity sensors, and there are a variety of these smart farms, as we call it, that employ these devices that can send data either to edge nodes or the cloud to do, different kinds of processing and get either health checks on the farm or to just generally track different metrics of the plots.
And what are some of the opportunities to apply machine learning in an agricultural context? What kinds of problems are useful or solvable in today's world?
I would say that for the opportunities in machine learning, we pretty much see things like anomaly detection being pretty big. Let's take, for example, temperature sensors, right? And we're tracking the temperature of various positions of our farm and, using that to correlate to the health of the crops. I think knowing what anomalies are being detected or if there's an actual issue with the temperature dropping too low, things like that. So applying machine learning in that aspect to find out what are the true problems with the farm, whereas it's just a sensor artifact, I think is a big area of interest in that space.
Yeah, so we are a part of a big project here. It's called the Wabash Heartland Innovation Network, or WIN. And this is funded by the Lilly Endowment. It is a $40 million project, which is to do with making both manufacturing as well as agriculture digitized in this Indiana region. It's a 10-county region around the Purdue University area. And a big thrust of both colleges of engineering and ag is that, can we connect the various farms that are there in this region using sensor nodes that are deployed in the fields of these farmers. So we have actually been using both experimental farms as well as farms in this 10-county region to sensorize them. And what we are then doing is we kind of have a living test bed where you have these sensors deployed in various forms in this region. And then we are also connecting these to, we have a dashboard of both these sensors deployed in farms. And then we also have drones that we have purchased. And then we have an embedded testbed. So I can explain the various aspects of it. But the high level dimension is that having a connected ecosystem of farms where the farms are generating data. This data is obviously multidimensional. And so you will see, for example, in our paper, we have data that has been collected using humidity sensors and temperature sensors from sensors deployed in these farms. So in addition to that, we'll be having carbon sensors that will be deployed. Then we have nitrate sensors. So essentially multidimensional data sets that are being created from these real farms, in addition to experimental farms that are there in the Purdue University area. So essentially digitizing agriculture by having data sets and then driving the data from these sensors to make the right decisions for the farmers.
What sort of experiments go on an experimental farm?
So since I'm a data scientist, my role is to basically have this end-to-end pipeline, right? So let me give you some examples. So a few things to keep in mind is, one is when you have these sensors being deployed in these agricultural fields, they have to be ruggedized. So that is something that you don't realize as a computer scientist or even as an electronics engineer, that you go into farms and you deploy sensors and you think, oh, voila, we're going to get data. So that does not happen. So you will see in my website, and we have been learning some of this the hard way, that we have the Raspberry Pi has to be ruggedized, or if we have regular sensor nodes, for example, temperature, humidity, nitrate, all of that is being done by a company called InDesign. We also have Microsoft Research pouring in both sensor nodes as well as the data pipeline to be able to collect data from these farms. And ultimately, the goal is to have this end-to-end pipeline. So the way this data flow can be described is that data is being collected from these sensors, and then you have gateway nodes, right? So right now in our current implementation, the gateway nodes are simple Raspberry Pis, and these gateway nodes are aggregating the data from these various sensor nodes. So right now the connectivity again is LoRa, so long range connectivity. In future, you can have, NB-IoT, etc., various kinds of wireless connectivity, but the current connectivity is LoRa. So once you have the gateway node aggregating all these different kinds of sensor data from these various farms, traditionally you will have one gateway node placed in each farm, right? So you have multiple sensors. Think of one farm with multiple sensors. A gateway node, say in the farmer's house, which is basically aggregating the data from that farm. So farm 1 has multiple sensors and one gateway node. Farm 2 has multiple sensors and another gateway node, and so on. So ultimately, you have a gateway of gateways that is connecting to the database. So right now, again, our database is a MongoDB database, and then we have a front end using Grafana Analytics. So doing this kind of a multidimensional data aggregation from data from the farms.
Very cool. It's always been something I'm curious about, how data in a place like a farm where you don't think of as being data generating until you get all the sensors out there winds up in something like a MongoDB. It's got to be a lot of steps in that path, as you'd mentioned, a lot of equipment and whatnot. In terms of deployment, how do things like that fit together? Is it a lot of custom things, or are there industry standards that people are following with equipment protocols? What's sort of the general tech stack look like?
Yeah, so like I said, we are learning the hard way that a lot of this equipment cannot be the equipment that you use in controlled lab settings. So these have to be ruggedized literally. So we have 3D printers and we have these enclosures that are enclosing both the sensor nodes as well as the gateway nodes. And then again, like simple things like if you want LoRa connectivity, if between the gateway node and the sensor nodes, there is like, say, corn, right? This is Midwest. So you might have cornfields. So if you have high corn that is inhibiting the networking between the sensor nodes and the gateway nodes, we essentially have these long antennae, which will improve the connectivity. So things like this that you would not think of in a controlled setting, basically have to think of in a digital agriculture setting. One other thing to keep in mind is that inherently, because I'm an applied machine learning engineer, my goal is to make sure I am more on the data pipeline side. So one of the things that we have done, and this is actually a project that is jointly funded by both National Science Foundation, Computer Science Directorate, as well as Army Research Laboratory, we have set up an embedded testbed. And this embedded testbed is kind of, you can think of this as the future of digital agriculture, right? What would a future farm look like? So in here, what we have is we actually have a whole bunch of NVIDIA devices. So SoCs, system on chips. Currently, we have multiple of 4 different kinds. We have NVIDIA Jetson Nano, We have NVIDIA Jetsons. We have NVIDIA Xavier. So Xavier is actually the one that is there in self-driving cars. So we have 4 different capabilities of these SoCs, or system and chips, that are connected in an embedded testbed that we use for controlled experiments that could be mapped later on to these living testbeds. So when I say living testbeds, is referring to the sensors and the gateway nodes and the forms, whereas my embedded testbed is this, sophisticated controlled testbed where we can run various experiments, such as the object detection and other computer vision experiments, and then think of mapping them later on in the ruggedized farm setting, where you have to think of additional things in addition to just the computational aspect of the sensor nodes and the gateway nodes.
Yeah, that's a very interesting aspect of edge computing that I think a lot of people don't realize because it seems so obvious. What does edge computing mean? Well, there's a computer out there, but it's not just a dumb, thin client or it could be, right? A dumb, thin client that just sends data to the cloud, but it can be a whole lot more than that. Most of the time in machine learning, we kind of think like, oh, big training data, big compute, maybe not as good at the edge. How does it work to do machine learning at the edge?
A nice point here is that people say that, is it going to be like edge in the future and the regular vanilla cloud computing, is that going to die and give way to edge computing? I would say, and this is not just my saying, people believe that it is very important for this kind of a decentralized edge ecosystem to survive and flourish hand in hand with this cloud centralized ecosystem. So if you think of our embedded testbed / living testbed, right? So we have a living testbed where you can think of everything being deployed in the farm and more inexpensive devices, etc. And then you can think of the embedded testbed where we have more sophisticated devices, right? So on the one hand, let's think of the living testbed to make this a little more appealing to visualize. So in the living testbed, you will basically have data that is being generated at these sensor nodes. So one aspect of the edge, so let's consider 3 different partitions here, right? And the reason I say that is because the first partition is something that is front and center in my lab, and that is doing in-sensor analytics. So think of on-device computation / in-sensor analytics, where you don't want these sensors to just be acquiring all this data, but you also want them to compute the data to some extent, right? So this is your sensor stack. Then you have the edge stack, where you can think of all of these gateway nodes, etc., that are aggregating and potentially intelligently aggregating all the data sets that are coming from these sensor nodes. And then you can think of, the cloud. So the cloud may have databases such as MongoDB. Either some of it may be hosted on premise and some of it might be on the cloud, right? So in this setting, again, you can see that there is this coexistence of in-sensor analytics on one end of the stack, edge analytics in the middle of the stack, and cloud analytics at the other end of the stack. So if you think of, for example, a self-driving tractor, where latency is going to be of prime concern, and if you are possibly irrigating the field based on the dryness in the field, there you might have to take real-time decisions. So you have sensing and actuation. So a big thing about cyber physical, and even in the CPS size directorate of NSF, where I review and write proposals to, a big thing is not just sensing, but can you take intelligent decisions by actuating the sensors in response to the sensing? So if you think of these sensor nodes, they will sense the nitrate, say, or sense the moisture in this case, and then actuate in response to the dryness level in the soil, right? So these decisions have to be taken at real time. But there might be other decisions where, this is something maybe of interest to the data scientist, right? Where potentially I want to aggregate data from multiple farms over time, say over 5 years, where I'm okay with the data flowing to my MongoDB database and just collecting various kinds of aggregation statistics that I can collate over time, do this over time, right? So there, latency is not of high concern. And there I basically resort to the cloud because throughput is something that I'm more interested in. So I think just through this example, you can see it's not just about cloud analytics or edge analytics or on-device computation, but there can be this thriving of these multiple aspects of computation along the partitions of device, edge, and cloud.
Yeah, actually, piggybacking off of that last point about throughput as well, another dimension that really motivates the need for machine learning at the edge nodes is also scalability. So the number of IoT devices are increasing every day for various kinds of applications, and trying to aggregate all the data and then take decisions, like Professor mentioned, could be very time consuming in a latency sensitive case. So that scalability aspect of having to take quick action on every single sensor node that we have is, I think, also very critical in that aspect.
Absolutely. One of the challenges I think a modern implementer would face is decisions about so many of these trade-offs, the cost, the latency, the efficiency, and every use case maybe has a custom need, so you have to kind of go in and make some decisions. But that also almost demands you give a tryout of lots of different ways to compare. So I think research like what you guys did, benchmarking some of the commercial and open source solutions, is really useful, broadly speaking, to people who are coming at this space. Could you, I guess, set the stage, describe the benchmarking you guys set out to do? Why was it useful, and what was the scope of the project?
So just at a high level, I think we set the stage perfect that, you have the IoT era where you have lots and lots of sensor nodes, and you basically need analytics to be done at the source of the data, which is closer to the sensor nodes and at the edge potentially. And then you also need some of the high accuracy, non-latency sensitive data to be analyzed at the cloud, right? So we thought on the one hand, there is the need to analyze some of the data at the edge. So there is this edge aspect that we explored specifically by using the AWS Greengrass, which is the IoT orchestrator for Amazon, then Google IoT and Azure IoT. So you have Microsoft, Google, and Amazon, they have their IoT orchestrators. So that was the edge part of our benchmarking. And then we thought the cloud part is also important, right, for other kinds of less latency sensitive workloads. And so we had this Amazon EC2, we had the corresponding versions for Microsoft and Google again. Right. So this is one aspect of the thing where we have edge versus cloud. And on the other hand, we had computer vision workflows. Now, for computer vision workflows, my lab is very interested in embedded computer vision. We are also doing embedded activity recognition. So some of these beefy computer vision workloads require, these really deep neural networks, right? So how do you optimize some of that on non-server class devices, that is embedded devices or mobile systems, right? So that was the other part of this paper where we benchmarked both computer vision APIs by, again, Microsoft, Google, and Amazon, and our in-house FRCNN-based object detection algorithm, which is actually now published in Census, ACM Census, and we call it ApproxDet. So maybe I will let Karthik give you some more details, and then we can follow on with the two aspects, the cloud and edge on the one hand, and computer vision on the other hand.
Yeah, so she explained it pretty perfectly that there are a lot of different parameters to consider, and there are also a lot of different options to consider. So the search space when you have a given application is actually really big. So that really motivates the need for benchmarking efforts like this, so that it's a sort of baseline to establish your decisions off of. And we consider, again, the two major workloads, which are anomaly detections as well as object detection. And so the motivation behind picking these algorithms particularly was that we wanted one to be a sort of data light or compute light algorithm, and then the other one to be a data heavy or a compute heavy algorithm. And this also plays to the different spectrum of algorithms and applications that people develop for. So we profile, kind of both these spaces to identify what works best in what cases. And then specifically about object detection, another added dimension is the cloud APIs or the service providers having their own pre-trained models like Google Vision or AWS Recognition and things like that. And so looking at their cost as well as their efficiency in terms of how quickly they're able to classify things, I think is a very interesting aspect given the application.
Yeah, so I will piggyback on that a little more because I think there are a lot of things going on, a lot of moving parts in this paper. So the way to look at it from a higher dimension is on the one hand, we have cloud versus edge, right? And on the other hand, we have computer vision. So we did benchmarking for these two broad areas, cloud edge and computer vision. And the reason we picked computer vision, like Karthik very nicely put, is because we wanted to make sure that we have a compute-heavy workload. And computer vision kind of typifies compute-heavy workloads. And not only that, AI and computer vision is a very up-and-coming market where a lot of the IoT market is dominated by computer vision analytics, right? So you have like video surveillance, etc., which is a very dominating part of the IoT market, right? So we wanted this compute-heavy, and we also wanted compute light. So for compute light, what we did is anomaly detection. So again, to kind of tie the strings there a little bit, if you consider IoT workloads, IoT workloads, you can think of it at a high level of being two different types that are very recurrent. One is anomaly detection, which is your compute light workload. It is not very computationally heavy. Another is, if you're doing video surveillance, etc., you have computer vision, right? So these two, the anomaly detection and computer vision workload, they happen a lot, and they might be, the bulk of these IoT workloads. And that's how we thought, the overall idea was, what are the kinds of technologies and what are the kinds of workloads that are very dominant in the IoT market, and profile those from both a commercial aspect and from algorithms that are being built in our laboratory. So that was the high level insight behind doing this benchmarking study.
And I guess as a way of stressing the use cases at the edge, what's the argument for not just saying, hey, send everything to the cloud and they'll figure it out at the mothership, I guess?
I think that is something that we wanted to leverage by using our computer vision workload. So if you can imagine, if you have these IoT cameras everywhere, right? And video surveillance, like I said, is a big part of this IoT market. So if every camera is going to be sending its data to the clouds, then you can imagine what's going to happen to the bandwidth, right? So that is one. The other thing is, we have a project in battlefield IoT with Army Research Lab. And obviously, these are very latency sensitive, right? So if you want to take real-time decisions in the battlefield, you obviously want to, if you see something that is out of whack, so say video anomaly detection, then you might want to actuate your decision as fast as possible so that something untoward does not happen, right? So one is that latency aspect. The other is the aspect of, not hogging the bandwidth. And the third one is what Karthik pointed out, right? Scalability. By able to have this decentralized model, you're actually using these multiple edge devices. And when you look at these edge devices, there is the concept of managed edge. If you're very concerned about security, privacy, and, what would be a type of edge device that is being used, can you, have some confidence level attached to the edge device, then you can think of it as the managed edge that is being provided by these different AT&T, etc., these providers. And then there is the unmanaged edge. When I say unmanaged edge, it's pretty much like bring your own cell phone. So that would be an example of unmanaged edge. So you basically want to use as much of the compute that is lying around there. So I would say three things. One is not hogging the bandwidth, using especially these computationally loaded workloads such as computer vision. Second is to do scalability, right? To actuate scalability by using as much of the edge devices as we can. And third is, very importantly, that people typically think of when they do edge computing is to leverage the ability to take quick light speed decisions by not having this latency associated with data transfer from the edge to the cloud.
One way to look at this is to recognize that all three of the big cloud providers you guys benchmarked have access to a lot of data and a lot of resources and good engineers and scientists and whatnot. Maybe trying to do something at the edge is a David and Goliath situation, although they're solving a general problem, right? They're not necessarily experts in agriculture the way you are. What's the current state of the art for their off-the-shelf products? How easy are these for developers to use, and what's the service like?
Most of these big service providers all have, again, as you mentioned, giant data sets, right? So they've been training their models over years and years worth of data with, millions of users pouring their data into it. But as a consequence, most of their models are very, very generalized. The top three, Google, Amazon, and Microsoft, all provide features like face detection, content moderation, text detection, optical character recognition, things like that. So there are many of these common aspects that they try to optimize for. But looking at more application-centric aspects, especially like agriculture, they offer a supplemental service where we can train our own models. So once we start going into that, that involves a little bit more developer complexity as well as knowing more about the space. And at that point, we reach the trade-off of having to work with their APIs to get our custom result or just get our custom result on our own. Looking at the very general case, these APIs are pretty easy to use. It's you send an HTTP request and you get a response back. So all of them have these very simple interfaces to do inferences. But again, for these custom labels and these custom applications is where the hardship comes in, and we kind of profile what the services can do as well as what we can do and the trade-offs that we can get by implementing our own algorithms, even off-the-shelf open source algorithms, right? So it doesn't have to involve too much developer complexity, but still trying to have that level of customizability in our solution, I think goes a long way in determining the price to effort ratio.
continuing in that same vein, so I think the commercial, if we just consider the computer vision APIs, right? So we looked at Amazon Recognition, for example. So all of these APIs, they are very seamless to use. But if you really don't want black box style APIs, right, where you can do various things, for example, if you have very specific requirements for your accuracy. So if we consider computer vision, for example, we do computer vision on edge and on embedded devices. IO intersection overlap is something that is used as an accuracy metric for computer vision workloads. And then there is something called mean average precision, which is what we've used for our accuracy. So if you see in our performance and cost metric profiling for the APIs, commercial APIs versus FRCNN variant in our lab, what we have used is mean average precision. But the way you calculate that mean average precision, it can be customized in a white box solution such as ours, right? Whereas the APIs, one, you don't know what the accuracy is. So you have to kind of go with what they say it is. The second thing, which is again latency related, is if you kind of want to run these computer vision APIs close to the data, it might be hard to control the backend. Whereas in our case, we actually call our in-house algorithm proxdet, because it at runtime can, as per the latency, it can quickly change the approximation level of the algorithm. We can talk a little bit about that if you're interested. But proxdet is what our in-house algorithm is. And the way that we say proxdet is advantageous over some of these APIs is it's very customizable. So you can customize the accuracy metric, you can customize the latency by putting the proxdet algorithm right next to the source of the data. And the third one is, cost-wise, right? So for the APIs, obviously, you have to pay at the rate of the vendor's specifics, whereas in this case, as long as you're running a proxdet on your machines or on the cloud, you would just basically pay for the compute cycles.
That's interesting in a number of ways. The one I'd love if you could expand on in particular is that sort of cloud versus edge deploy. That feels like an unsolved problem to me. I mean, many years ago, the Java programming language came out as an attempt to say, hey, we're going to have the Java virtual machine, just implement that in lots of environments. And Docker works the same way today, right? Are we at that level where it's easy to move your code over, or is this a lot of custom duct tape and shoestring kind of stuff?
Yeah, so there has been a lot of work in that space. And one of the products that we do profile, which is Amazon's AWS Greengrass, is pretty much what you just described, right? It's a way of deploying code out and systems out to the edge using their Lambda platform, which is, piggybacking off of their serverless or functions as a service platform. So what AWS Greengrass is that it's an IoT SDK for various kinds of devices that Amazon supports, which are most of the popular ones, like your NVIDIA devices, Raspberry Pis, etc. And they can run this custom development kit to be able to have easy deployments to the edge using a similar interface as it would be if you were deploying to the cloud.
Well, let's talk first about, we should go through all the benchmarks, but maybe cost. The cloud providers, I know it's cost per usage, so easy economics, maybe some discounting at volume or something. How do you cost out the other solutions like open source stuff?
Yeah, so the cost model of open source depends on where they're run, right? Either there's the initial operational cost of setting up our own servers or running them on different cloud services, which we have done in our evaluation in the paper. So we picked the three popular instances that are used for Amazon, Google, as well as Microsoft, and we run our custom solution on that. And the cost that we report there is the cost of the virtual machine itself. So that can be amortized over, multiple runs or, multiple different devices. So I think that sets a good playing field with respect to these other commercial offerings that have a more pay per request model.
Yeah. So on a related note, if you consider the Google versus the Amazon IoT orchestrators, so one of the advantages of Google's IoT orchestrator is that it is basically taking into consideration the number of devices. Is that right, Karthik?
Yeah, there are obviously a lot of differences between these IoT frameworks. And the framework for Amazon is that you typically pay per device in your IoT infrastructure, or you pay per messages sent and things like that. So the granularity with relation to Amazon is a lot smaller in terms of your workload. So if you have, let's say, fewer devices overall, but very large messages, Amazon's IoT orchestrator might be a better fit. Whereas in Google, you pay per megabyte of message sent. So Google doesn't care about the number of devices, it just cares about the data that's being transferred. And so again, that motivates the use for that if there are lots of devices, but very small sized messages like heartbeats or things like that. And then Azure, on the other hand, optimizes for something what they call a unit. And so they have a flat amount per unit. And a unit is a single IoT hub that can have any number of devices. And a unit is kind of capped by the amount of requests that are being sent. So it's a kind of a number of devices plus a number of messages kind of mixed model. And so if there are lots of devices, but the number of messages are varying, I think Microsoft's Azure would be a strong suit. So there's a lot of these different granular pricing models that are influenced by the application.
I'm glad, we solved that puzzle about Google versus Amazon, because I think Google's way of doing things where it's based on data, the pricing is based on the data sent versus the number of devices. So in Google, it's basically as per the amount of data set. So if you have multiple millions and millions of IoT devices, I think it would make sense to use Google's IoT orchestrator. And to give you a little bit of perspective there, I think this might be actually a very exciting statistic that I found from Gartner's 2019 report. It's almost like an IoT device for each person on Earth. So if you think of originally in 2018, there was about 3.96 IoT devices for 7.63 billion people on Earth. Whereas in a few years, in 4 or 5 years, that's going to become 25 billion IoT devices for 8.18 people on Earth. So think of this number. So you have 3.96 around 2018 IoT units in billions versus the world population is 7.63 billion. And in 3-4 years from now, it's going to be 25 billion IoT units for about 8.18 billion people on Earth, right? So you'll have so many IoT devices. And if you just consider a living testbed, right, where you have this living lab with multiple IoT devices, I think it would make sense to just consider the price as per the data that is being transferred from the edge to the cloud. And that is essentially what Google does. Amazon's current model is based on the number of devices, whereas, like Karthik mentioned, Microsoft is basically a combination of the two, which might be kind of a nice way to go about it if you're a smaller sized location and you have expensive sensors and you don't want as many IoT devices / sensors to be distributed across your facility.
Well, we touched on cost. Let's talk on quality, I guess, or which maybe we would reframe as accuracy. What were you trying to measure in terms of the overall goodness of these, and how did the various options turn out?
So I'm kind of excited about our in-house solution, obviously, right? Because that is in-house and that is something that we have designed, keeping in mind the very constrained resources that may be present on these SoC, system and chips. I keep saying SoCs, and that's the acronym that is well known for system and chips. Let me introduce a proxstat, which has been kind of interspersed in this paper, JANUS. But we have a new paper from last year from ACM Census, which is a top computer science conference, and it's called a proxstat. So a proxstat is what our computer vision in-house solution is. And that is where I was saying that accuracy is very customizable in a typical white box algorithm for computer vision. So to give you a little bit of a specific concept into a proxstat, what a proxstat does, it does approximate object detection. So we are doing object detection rather than object classification, although we have come up with variants of a proxstat for both object classification and activity recognition. But to just go along with object detection, to just keep the flow, number one, it is a computationally heavy algorithm, object detection. It is heavier than object classification, but lighter than activity recognition in the computer vision spectrum of things. And accuracy in the case of object detection or many of these computer vision algorithms is measured by something called IOU, intersection over union. And then typically you take this IOU as your accuracy kernel. So the metric is the basic metric for these object detection algorithms. And then you take something called MAP, which is the mean average precision, which comes up here. So it might be hard to actually see what is the accuracy of these commercial APIs because they don't give you a number. So to give you a little more of an insight into what this accuracy means. So in object detection, you're not just saying that there is a cat or a dog in the video. What you're doing in addition is you're creating a bounding box. And in the bounding box, think of the bounding box as the bounding box that a proxstat is giving versus the ground truth bounding box, say, for a cat, which is there in the frame, right? So if there is very good correlation between the ground truth bounding box and the bounding box given by your algorithm, say if there is 100% overlap, then that is a perfect accuracy. Without going into the details, the IOU, intersection over union, will basically be 1. So think of the two bounding boxes overlapping on each other exactly. For various algorithms, you might have like a threshold for this accuracy metric. So typically, I would say 50% to 60% might be good. So this kind of customization you cannot do. You cannot get the accuracy metric for one, the value for it. And the second is you cannot do any customization based on your specific domain-specific accuracy requirements, right? So in some domains, you might need a very high threshold. You might need, for example, if you're doing a cell biology experiment, you might need the overlap to be very high. Say my bound could be, or my threshold could be 80%. Whereas if it's a coarse granularity measurement that you want, you might have a bounding box overlap of 40 to 60%, right? So depending on the domain. So this kind of customization cannot be done in your commercial APIs. The second thing, which I think is very cool about our algorithm, our approximate object detection algorithm, is that at runtime, right? So at runtime, taking into consideration both the content of the video and the contention. So I'll come to that in a second. So it is both content aware and contention aware. And what it does is by using a whole bunch of approximation branches, it comes up with the right approximation to use for the specific content and contention present in the current circumstances. So let me give you an example. Say if you have a soccer game going on, right? And there are like players moving all over the place and it's, a very happening game, right? So you have very fast moving objects. In such a case, you might need, a higher accuracy, talk about accuracy in a very broad way, right? Whereas if you have a very static video, you might not need your object detection algorithm to work at that level of accuracy. So depending on the content of the video, we at runtime pick what level of approximation to give to our algorithm. That is one thing. And the second thing is contention. I think that is a very important thing to consider in the embedded / edge space, right? So if you consider a server class machine, there is very clear isolation between resources. So resource isolation is very nicely done in a server class machine. Whereas if you consider these SOCs, the resource isolation is not done as well. So if you have, say, background tasks or co-located applications running at the same time, it might be really hard to do resource isolation in a proper manner. So what happens is the contention, because of these contending application, might feature in a very unfriendly manner to the prime application that you're running on that SOC. So in this case, say object detection is your mainstream application that is running on your SOC. And say if in the background, you're trying to do some anomaly detection or what have you, but since object detection is a GPU intensive task, say you're doing some other GPU intensive task, such as listening for some bad guys, right? So say your voice assistant is trying to make sure there is no bad guy coming for whatever reason. So that is also a beefy task, right? So that would also eat up your GPU. So the ultimate resources that is available for your SOC to do object detection will be lower than the real GPU availability by the SOC, right? So the contention and the content are two criteria that may affect the approximation level required for the object detector. And what approxdet does, it does approximate object detection by taking into consideration both the content, the video content, and the available resources on the mobile system or the SOC. So I think this kind of runtime adaptation to both content and contention, it's basically the only thing on the market. When I say market, I mean the academic market. And obviously out there is nothing out there that does this kind of joint optimization. So that's what approxdet does. And the reason this is relevant to this paper is we did not have this approxdet paper accepted when this initial paper came out, but the FRCNN kernel that is used as the object detector for approxdet. So if you see, there is one of the knobs that we have shown in this paper is the number of proposals. So the number of region proposals is an approximation knob. So if you have a higher number of proposals, the accuracy will be higher, but the approximation will be lower, which means your latency will be higher. So a high latency is bad and a high accuracy is good, but you can't get both at the same time. So you might have to cut down on latency by also cutting down on the accuracy some. So we can go a little more into that, but the FRCNN kernel, which is faster RCNN, is the kernel that we use in our approxdet algorithm. And one of the very important approximation knobs is the number of region proposals that we can quickly vary at runtime based on both content and contention.
You guys had discussed there were two kind of regimes you were testing, the image recognition case, which is obviously data rich, and then the outlier detection case, where you're looking at the temperature and humidity data and applying extreme value analysis, presumably much lower in its computational demands. How does that sort of change of constraint affect the results you guys got during benchmarking?
As one would expect, the data light workload would have a faster runtime as well as lower data passing time, which is the amount of data that's transferred over the network. So more than comparing both these kinds of workloads, we're comparing in a given workload all of the different options that are available. And something else to note, which is one of the differences between these two, is that things like anomaly detection or even extreme value analysis is commercial support for just directly pre-implemented algorithms, which are very popular for object detection and computer vision, is not really that popular for these data light workloads. So they involve a lot more developer intervention and some developer programming that is needed to be able to implement these on the edge nodes. And so what we see pretty much in our evaluation of the data light workloads is that based on the choice of where we are running, obviously the cost changes, and we see that when we run these on the edge node itself, our costs can be offset by the pricing models of these IoT orchestrators. So like I mentioned before, the pay per megabytes of data transferred or pay per device comes into play, whereas when we're looking at these big cloud virtual machines, on the other hand, they have a lot more upfront cost. For example, Amazon and Google both have a virtual machine payment model of a minimum of 60 seconds, while Azure VMs have a minimum of 1 second for their billing granularity. So it again goes back to the application to be able to use these resources for the amount of time that they're being provisioned for. Otherwise, it would lead to stark losses and unused capacity. Whereas for the cases where it's an IoT orchestrator with the code running on the edge device, it's a little more configurable in that sense. And then something else that I briefly touched upon earlier is that we also profiled this data light application on a serverless framework, which functions as a service for Amazon. And that adds another kind of dimension to this, because in a serverless setting, the user doesn't have to provision any virtual machines or provision any servers for being able to run the code. The cloud provider, and in this case Amazon, pretty much takes care of that. All the developer has to do is set the memory sizes, and the cloud provider provides things like reliability, scalability, fault tolerance, etc. So there's a bunch of these guarantees that the cloud provider is able to give the developer, and all they have to do is write the code. So it's very much similar to running code on the edge device itself, except it's not, and a lot of this orchestration overhead is being taken over by the cloud provider. So what we see from the evaluation is that using AWS Lambda is very cost effective as compared to using these big cloud virtual machines and provisioning them ourselves and paying for the time that we're not using them. And on the object detection side of things, what we see is that for running our custom solution, it can be about 77 times more cost effective than using these pre-built cloud solutions, while the cloud solutions could have faster latencies of about 3 to 4 times depending on which cloud service is being used. So again, as I mentioned before, a lot of different considerations and a lot of different trade-offs in terms of either accuracy or cost.
Another thing to add there is, in general, people typically think that if it's a serverless workflow, you cannot use computationally beefy algorithms. So in our initial paper, in this paper, for example, we have not used computer vision in the serverless mode. We have just used anomaly detection algorithms in the serverless modality. But, in our follow-on work, we basically have decomposed computer vision workflows so that you can use these beefier computational workloads in the serverless platform. And exactly what Karthick said, what that does is you do fine-grained billing where you're paying by compute time rather than by time per se. So it's very efficient for the client. And then again, you don't have to take care of any of the non-trivial setup. All of that is taken care of by the cloud vendor. But at the same time, you're just paying for compute rather than by time. So that is one aspect. And the other thing is by using our runtime approximation, for example, by Proxtet, and this is something that we profile in the paper, is that we reduce the runtime over the commercial APIs by about 57.3% at the cost of a 9% accuracy drop. So saving latency-wise about 60% with a 9% accuracy drop is a big win, especially if you have a latency-sensitive application. So you can do very aggressive approximation if needed, depending on the SLA bounds for your accuracy and latency to get the optimal Pareto frontier for accuracy latency. So one is having that tunability, and the other thing is also being able to decompose some of these computer vision workloads to be able to run them as functions as a service in the serverless setting.
Well, to wrap up, I'd like to ask both of you about what you're most excited for your research direction going into the future.
So for me, I'm very much excited about the serverless space. I think that the opportunity that it provides to the end user to not be able to think so much about all these complicated aspects, of fault tolerance and reliability and scalability, which usually involves a team of people and everybody, having different kinds of expertise in these subjects. It bridges all that away from the developer and it lets them just focus straight on the application, straight on their code. And the developments in this space, like Professor mentioned, of being able to even decompose these large, heavyweight kind of algorithms and functions into sets of serverless functions is, I think, an exciting space. And there's a lot of optimizations that can be done. And that's pretty much what I'm most excited for.
Some of that, serverless work that we're doing together, having these disaggregated operating systems. So in serverless, essentially, you have Amazon S3, right, which is acting as your disaggregated storage. But then there is a lot of data transfer optimization that we're doing that, how do you basically make that disaggregated storage smarter to be able to run with various kinds of diverse serverless workloads? Because as you move on from the vanilla cloud providers to serverless, one of the things that will be very fruitful is to be able to run regular applications that were not initially meant for serverless in a serverless savvy manner. So can you make changes? For example, serverless is considered stateless, right? So can you have the right level of statefulness so that you can run applications that require some statefulness? So that is one very exciting part on the data engineering side. And on the data science side, I think given that we have access to both these living labs and very sophisticated SOCs, one of the things that my lab is very interested in doing is how can you run these really beefy neural network applications on these resource-constrained devices. The vision of my lab is to improve this on-device computation by making this computation efficient. So in a lot of ways, making them energy aware. Right? So how do you improve the size of the neural network based on the size of the compute that is available to you? Doing distributed training, we are using federated learning, for example, to use all of these different devices as part of this training process. Of course, distributed inferencing is also very important, right? But novelty-wise, I think on the research side, a lot of the problems are solved in terms of distributed inferencing. And that's a distributed training where you can bring your own device and use federated learning to use these various devices, which may be in different forms and factors. So that is another aspect that I'm working on. And then again, decrease data transfer costs. Can you come up with intelligent ways to do on-device computation while decreasing the data transfer costs using some of these communication costs such as LoRa? So LoRa might kind of drain your battery faster. So can you decrease some of this communication by using some smarter algorithms? So I would say a vision of my lab is that when you have these fast proliferating sets of nodes generating streams of data, can you armor these sensors to not just collect the data, but to do some of this computation analytics on the data, on these sources of the data collection, as in the sensors, in-sensor analytics or on-device computation. And what will happen is there you will have both a mix of centralization where you have cloud analytics. And in the cloud, what we're doing is we are doing optimization so that you use the right kind of configuration parameters for the databases for these widely varying IoT workloads. And on the device side, we are basically improving the efficiency of these devices by right-sizing the size of these neural networks to work effectively on these devices. So basically using this entire gamut of device-on-device computation and cloud analytics in an efficient manner.
Well, very exciting areas I look forward to following up on. Where can people follow you guys online and especially get details about the lab and Proxtet and some of the other tools we talked about today?
Yeah, so I have a website, Chaterji.io. I'm also on Twitter. Tend to tweet every time a paper gets accepted. So that's a good thing.
And for me as well, Twitter is pretty much the space where I put details about all of my research and all the papers that get accepted. And that's at Karthick_SH.
We'll have links to all that in the show notes. Thank you both so much for coming on today and sharing your work.
Yeah, thank you so much for having us.
That concludes this installment of Data Skeptic Consensus. Our guests this week were Karthick Shankar and Somali Chaterji. Claudia Armbruster is our associate producer, Vanessa Burciaga does guest coordination, and I've been your host, Kyle Polage.